Draft, whoops. Yeah, alright, time for another DraftScience video presentation. Anyway, so I will get to this video, which will be some draft conversation about the whole nature of what charge is. And it's got lots of little pieces to it. So every subject has, all these subtle little details. So that's why this all takes so much time, is because there's always, what about the blah, blah, blah experiment? What about that? What about, and it's the annoying part of all of this is that, any explanation has to be able to fit all of these different outcomes. And even conventional physics just, they drop the ball all over the place in terms of tying up any of those loose ends. As I've pointed out with the kinetic energy formula, they just don't have a single experiment that says, there it is. It's really obvious. They don't have one single experiment. They don't have any evidence of this extra energy being produced. The violation of Newton's third law in principle completely. I mean, what's the point of Newton's third law if you're going to say 2,000 joules goes that way and 2 joules goes that way? There's no third law anymore. It can mean anything. Alright, so yesterday's video, polarization came up, and I tried to say, in some sort of coherent way, consistent with the video's progress, without ruining it, by going, stammering through it, that gratings, okay, where you use wires to detect polarization, is different. Okay, there's different ways to cause the same effect of separating light. So I tried to make the point that a prism is doing something different than the wires are doing, and fundamentally, for light, very different than the filters we actually use that they call polarizing filters, a polarizer. Because it's really not doing the same thing. Even though it has a similar construction, it's really not for the same purpose. So a polarizing film, the whole intent is to get as much light as possible. And so another thing to understand about light versus, say, radio waves. Radio waves are antenna, okay, polarized. That is in the sense that the antenna, I should draw it like a traditional antenna, is that the polarization is sort of dictated by the orientation of your antenna. And so we can see the antenna, and they're always oriented in the same way. We can only produce it from the single, we can have multiple antennas and then create energy at different places, but obviously we're going to dilute how much energy is in any one orientation, and that's going to really make for a very weak signal. So so the argument is that the polarization of radio waves is usually produced by a polarized antenna, which means it's already polarized going into any kind of filter. And it makes a big difference if you're already polarized going into the filter, then you get lots of effects from the filter. Just turning it a little makes a big difference. If I had unpolarized light, for example, and I put it through a grating, I'm not going to get nearly the effect, because any way I turn it, I'm going to be I'll be this orientation or this orientation or this orientation. The light will have every orientation in it, so I won't be able to see any effects, because all I'll be changing is which photon I'm manipulating or changing with the filter. So all I'm doing is changing which one. I'm not changing how many. So this is sort of important stuff to recognize. So anyway, so the optical polarizers aren't really, the polarization, you could look at it this way. You could say that, say if you were doing this with microwaves, and you put it into the metal filter. Okay, so your microwaves are going out, and they're going to go through this filter, and you could turn the filter this way or this way, with the or against the polarization of your signal. What it's really, I would argue, is doing is there's places where the signal goes, pieces of the signal go through, and then places where they hit the metal. And if they hit the metal, what's going to happen is they're kind of going to go through the metal. They're going to vibrate, because it's a small piece of metal. They're going to vibrate the metal in sympathy with the signal you're sending in. So you're basically just you're using one antenna to extend the signal. You're not amplifying it. The signal goes in and it comes back out of the piece of metal. So if it's a small enough piece of metal, you can keep it, it'll transmit your signal, essentially, effectively. But it's also going to reflect some of your signals, so you're obviously going to lose some. But so what's the consequence of transmitting? Well, the consequence of transmitting is that you get a phase shift. So when something goes through a surface, it phase shifts when it goes from the lighter density to the heavier density, and it doesn't do it from the heavier density to the lighter density. So you get a phase shift when you transmit. So if you push something through something, there's always a phase shift when it comes out. Because of the first surface transition. Now, I would argue that it's phase shifts in multiples as it's going through the stuff. That's the real phase shift, and it's just does it depending on the frequency of your light, depends on what amount it slows you down. So the speed that you go through the substance is really causing the phase shift. And the phase shift can be many multiples of your frequency. So that is, you can be your shift can be many phases off. Okay, like the first bit goes here, and then the other thing is sending a bit way back here, a second later. But those two things will end up back in phase, in the sense that if you just fill in everything in between them, you're obviously got back a complete tune, so to speak, a note. Anyway, so the really phase shift is more important than the path length difference. So I'm just trying to say that there's two ways you can change the phase. Okay, that's all that really needs to be said. You can change something's phase by having two locations, all right, and having a path length difference. So your phase is going to be changed because this one's being delayed because it's taking a longer path, right? Or you can shift the phase by merely forcing one thing, okay, to go through a medium. So the point is that the optical filters aren't really using bars. They're using a place where there's twice as much. That is, there's two plastic surfaces, in places where there's only one plastic surface. So the idea would be, as the light goes through the pieces, some pieces go through the two layer, they have a phase shift that's twice as much as the ones that just go through the one layer. So they're all going through the layer of plastic. You're not wiping any of them out by sending them in eccentric directions, and what you're doing more than diffracting is you're just phase shifting. So you're getting the same effect of a delay. So the same stuff going through the same location can, very close locations, some of it is slowed down getting through the polarizing material. So it's as if you moved an object from here to here and then made it go through. It's essentially a longer path because it's a slower path. So if you just thought of it that these two layers equal takes longer to get through them, you move slower, okay, it would be the same thing as a phase shift. So I'm just saying you don't necessarily have to change the path length difference. Is not as relevant when you're changing the path what it has to go through. And so the end product is always about affecting the phase. That is how the bits are aligned. Okay, so when you have this necessity that the bits have an alignment that's consistent, that this period is the same. So you can't replace this one with this one because it's out of phase. It won't be in the right place. So when you're mixing these pieces and you're going to put something back together again, you need these pieces to be in the same alignment. So now, if you change the path length of this one, well, let's say you change the path length of this one, slow it down, then this one will be able to fill this void. That's the point. So the necessity of the phase being the same is just meaning that that's how I can make all these different photons that are going to be broken, essentially. You're going to have pieces that are moved to different phases. So this one hits something, slows down, ends up being 2 of them in this location. That kind of thing is happening. So all the bits are being adjusted. Or you can just change, again, their path lengths. And if you change their path lengths, it's the same thing. As long as you arrive at the right location at the right time, you can remake a photon. So it's just about location and time. And you can change when it shows up based on slowing it down. Don't like that language much. Slowing it down by forcing it to go through a medium that creates the path length. You could argue that the medium is what's creating the path length, because it's really the force has to force electrons to exchange their pressure, and that takes time before the photon is recreated, the bit is recreated. The electron moving, the last electron moving, it takes time to you hit one electron on the one surface of the glass. That electron has to move other electrons by moving closer and closer to each other. That's the distance and the time delay. And but the outcome is going to be the same, in the sense you're going to move an electron. So you moved an electron on the interior, on the surface you hit, and then by moving an electron on that surface, you end up moving an electron on the other surface, but there's a delay in the time that movement takes place, and that changes the phase, changes the position. All right. So that's probably just to clarify there. You can't really talk about using wires or threads as a filter, a polarizer, and this method, because the two have substantially different. This one is so much better at preserving images than this one. And yeah, and the key point is it's hard to create light that's pre-polarized without putting it through a filter. So the only way you can already pre-polarize light is to say, I'll take a light and I'll just cut half of it out. I'll lose half of its intensity to make sure I have most of it's polarized in one direction. But it's not going to be polarized perfectly. So not like an antenna. An antenna is a nice straight line, produces one polarization. We have to artificially make light polarized, and it's not necessarily perfectly polarized. Now maybe the light from the sun is, glare. So if you use glare, it's probably really good light in terms of it being all polarized in the same direction, I think. I'm not sure of that either, though. So I won't say it. Just forget I said it. All right, so anyway, just wanted to, all these subjects, again, like I said, they're a little, there's subtleties to all of them, which is annoying, and which I have, in some sense, I think, reduced it to something more simple, but it's still mechanically, imperfect. The model doesn't illustrate it perfectly. Well, that's just a matter of time, frankly. I think the understanding the photon as little bits is working. Okay, it's just that we have to understand the little bits in terms of hitting electrons and then moving electrons and then being reconverted back into little bits by the electron moving into the universe of energy. So that gets us to charge, which is essentially very similar. They're all connected. You can connect gravity to charge fairly easily in understanding it's about something known as pressure. And then pressure would be something like gravity, because the deeper you go into a gravitational object, the higher the pressure gets from all of the fact that the atoms are compressed. Well, first the molecules, the compounds are compressed, and then the atoms inside are compressed, and everything gets compressed. And that's why it gets molten. And blah, 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 blah. So we'll move on to this. But we'll wait for that to dry. So we'll take a little break. Yeah, back. Alright, so this is on electroscopes. So the idea is the gold leaf thing is the typical example. And so you have two little pieces of gold leaf, and if you can put a charge on their surface, then obviously they'll repel each other if they have the same charge. Except the idea is when they're not repelling each other, that is when they're just hanging down, they obviously have the same charge, but they're not repelling each other. So they have no charge, you could argue. And what would no charge be? So that's kind of, no charge would be there has to be an equality between the pressure of the electrons, the exposure of the electrons, and the exposure of the protons, which means there's no north and southness. The atoms look neutral. So that's what you're really saying. So there's an arrangement between the proton. This is how it's typically drawn, you know, is that you have the negative charges and you have the positive nucleuses, and what you're really doing, you know, and you could argue that this is a common thing going through the atomic structure, and that you push this electron in, that moves this one in, and you know, and then you end up with extra electrons over here, you know, more of them on this surface, and as you push them in and make the proton more visible, essentially. So as you could argue, as the electrons move this way, the protons don't have to move that way. They'll just automatically have more exposure. So if I can push the electrons in, I can make the protons more visible, is sort of the idea. So I guess a better way to draw it would be down here, because then you could sort of see the idea that the less exposure the electron has, the more exposure the proton has. So when they're neutral, they're in a position where from a distance away it looks like balance. So you're really just saying how much of the proton are you obscuring with your electron. The further out the electron is, the more it's obscuring your view of the proton. That's what I understand. The closer I put this chalk to you, the less of me you can see, and the closer I bring it, the more of the proton you see. So you're basically just saying, how much of the proton do I see? I see more of it the closer the electron is to the surface of the proton. So I would argue that that's a way to think about it. It's just that the proton is in fact just moving from a position here where both sides see the same thing, which is an equal amount of plus and minus. So from here, the viewpoint is neither plus or minus, you know, no charge. And then if I move this in, then it's going to see the positive. If I move the electron out, then it's going to see more negative. And so that sort of defines the pressure. And the pressure happens, the one that you can see is obviously the surface. You can't see in here. You can only see what's happening out here. So in here, that doesn't have to be happening beyond the fact that now these atoms have to absorb that change. So if this surface can't switch to opposite, and the whole thing ends up being a surface, like a round thing, then obviously the interior is accepting the extra pressure. That is, there's more electrons on the interior. And so there's going to be some will to get rid of that. Once you get rid of these extra electrons. So it's extra electrons that are creating the extra pressure. So it's almost like a gravity argument. The more electrons you add, the more pressure you create in the inside that wants to get to the outside. Unless it's like a conductor or something and you can just conduct it away. So that's sort of a way of describing it. Because you have these different things that the electroscope can do that, you know, make it, ooh, that's a little bit weird. So there's this idea that you can charge it, okay? So it's just a plate. Yeah, it's wet, but we'll draw on it anyway. Yeah, I probably should have done this bigger thing for the sake of clarity. But anyway, you know, and then you're taking whatever charge is on here and it's getting extended to the, like I said, he's using a needle, but it's easier, I think, to understand based on the little bits that will pull away from each other. You could make them out of lots of different substances, but anyway, when they're charged. So the idea is you can bring something charged towards it, the electroscope, and create a charge that's opposite, okay, whatever the charge it already has is. Now, but it won't cause a, well, yeah, all right. So the idea is okay. So you have the electroscope. You bring something that's charged near it. You don't touch it. So this is negative. Well, this surface turns positive. So the negative charge, that is the extra electrons, push on the electrons on this part of the surface and push them towards the protons, which means the protons are now more visible on this surface. But it just means that there's more pressure here, which means the electrons have to go here. And so that's what's causing the extra electrons here, is the fact that you push them in here, and they're popping out here, and then that's going to separate these two. And now you can touch it, all right? So you can ground it to get, and you'll basically pull off these extra electrons on this surface. Will now have a pathway to get off of this surface. So, you know, you're getting rid of ones that are now extra pressured. And then, you can take your finger off, and so now it's, it's neutral. I mean, it's happy. This pressure went away, so now these two leaves are going just straight down again because they're not going to be able to fight gravity with their repulsive pressure. And now you can pull this away, and now you'll separate again, because now you have the opposite effect. You basically took some of the electrons away that were this thing's electrons, this surface electrons. You took those went down here, then you pulled them off there, but they're still missing from here. And so now when you pull it away, the electrons want to go back on this surface, equalize this pressure, but there aren't any. So now it has to pull them back this way to bring them back on this surface. So there's still a deficit. Now you end up with positive charge here and repulsive charge. So, those little subtle experiments are what, makes it a little more complicated to explain what's happening, because it's not just as simple as you just dump electrons on a surface. You can't just dump them. But anyway, you're dumping pressure. So there has to be more pressure where you are to be able to force the electrons to want to leave. They have to want us to leave to go on to another surface. They can't just do it. Yeah, I think that's a way of saying that. But you're pulling them off of an insulator, which is another subject, right? Because the insulator can't, each location on an insulator is independent of all the other locations, so they can't communicate with each other. So if one part of the insulator has charge on it, it can't spread the charge, it can't move the charge, it can't do any of that. It just sticks right on that piece of surface. There's extra electron, and the electron isn't mobile. So you basically do have to say, I have to take that little piece of extra pressure and I have to touch it on another surface to get rid of that electron. Yeah, something like that. All right, so, there's lots of ways to explain this. This guy really isn't modeling, okay? He's just talking it, and I'm just saying the way he described this is fundamentally not too bright, in my opinion. So he's showing how light, that he can't, so he's trying to demonstrate the photoelectric effect, which is basically saying you're trying to change the charge on the surface with light. So he couldn't get anywhere using a very high-powered white light, and even a regular fluorescent bulb didn't do much, and so he had to use a high-frequency end of fluorescent, that is ultraviolet, to get there to be a charge on the surface, which meant he knocked electrons off the surface. Now, what he didn't prove was that the charge on the electroscope was positive. Because that's what it is, right? I mean, you're knocking electrons off, which means you're pulling electrons from the electroscope, and you're left with a positive charge. And he sure showed that by just bringing a negative charge, are more positive charge towards it. It would mean the little things go further apart if you brought a positive charge, and if you brought a negative charge, they'd go closer together. So he could have at least demonstrated that he actually did remove electrons. But he didn't do that. But anyway, so this is just the part where he's doing these light experiments, and then he gets to the part where he's talking about positively charged. So first he starts by negatively charging the electroscope to create extra electrons. So he's putting extra electrons on the scope and then trying to knock the extra electrons off. Now he wants to do it in the reverse way. So he wants to charge the electroscope positively. That is, he wants to pull electrons off of it. And then try the experiment. And the reason why, and so he just says this, I think, in a really sloppy way. And so we'll just play the second half of the video.
So when I rub this plastic against wool, it's actually going to strip the electrons off of the plastic so that it leaves this positively charged.
So because it's an insulator, right, the plastic rod, to get as much charge as possible off, you have to go to all the locations, as many locations as possible, to pull the charges off. Now, I don't know if we're doing it across the edges is the best way. It might just across the flat surface might work even better. But anyway, so that's what you're doing, is forcing, okay, the condition to match. And what he's really doing, because it's positively charged, is he's pulling electrons off the electroscope. So instead of putting something onto the electroscope, the electrons, he's now collecting them. So if he wants to collect them, he probably should just go across the flat surface to pick up as many of them as he can.
Now these positive charges, they can't be knocked.
So these positive charges, he's talking as if the positive condition of the atom is made out of some kind of positive charge, and it's really not. You haven't added positive charges. You've just taken away more electrons that makes the atoms now look positive. You've, in a sense, ionized them.
Loose as easy as these electrons, because the
see, so you can't knock the positives away, right? You're just changing the number of electrons. So there's a state where the atoms are all happy. That is, their electrons have the same pressure, and that would be ground. And so everything looks, you know, the same because the electrons are the same amount of distance from protons. You're creating the same exposure to the electrons as there is exposure to the protons. You see as much, if the protons were red and the electrons were blue, you see as much, you see purple. Purple means no charge. So when it goes bluer, because you added some electrons, now they're obscuring the protons, then it goes blue. And when there's too few electrons, then it tends to start going red, because now you see more of the protons. And that's, so you're really, there is no positive charge. There's just a ground state where you have an equal exposure to charge. Then you can change that state by just changing the electrons. So the electron, you're just changing the number of electrons. So the negative voltage is really just an absence of negative charge. How to say that? The negative voltage of a positive versus a negative voltage is just a difference in the electrons, the number of electrons. The real zero isn't is just less electrons. The ground isn't a real state. It's just a state of balance between the number of electrons is the right number, so you see the proton and the electron equally.
positive charges are really large. They're the protons in the nucleus.
Right, so you're not going to knock those out anyway. There's no hope of you knocking those out, and that's not why you're in this condition in the first place. You're not in the condition in the first place because you added positive charges. He didn't add protons, so he can't knock protons off. It's not at all the same as the other side of the, when you added the negative charges, then you were going to knock the extra negatives off. You can't knock extra positives off because you can't add extra positives. You can only take away more electrons, and now obviously you can't eject electrons easily because now you have too few electrons. So you have no hope of knocking the electrons off. So it wasn't that the protons are hard to knock off, it's that the electrons now that you have are really deep, and they're not going to be knocked off because they're closer to the proton, they're well bound. You know, when you have too many electrons, the surface electrons are higher and therefore weakly held. The more electrons you have on the surface, the more weakly they're held, and the less you have, the less, the more strongly they're held, and that's all it really is about. That I think is the more accurate way to model this. To talk about knocking protons off is almost ridiculous.
So the atoms. Let's try to discharge this with the UV light now.
So this is the light that worked when you were trying to knock electrons off of a surface that had a lot of electrons on it. Now it has very few electrons and you're trying to knock them off. Well, you're not going to be able to knock them off because you have fewer, and they're more tightly held because now they're much closer to the protons. That's why the surface looks positive. It's because you move the electrons much closer to the proton, which means you see more of the proton.
So you can see that nothing happens.
Quite sensibly. Yes. Consistent with a reasonable theory that it's all just about the number of electrons, and this really doesn't have, the protons can't play. The protons are a victim of the circumstance. They are not part of the circumstance. They don't do anything. Okay, if I move the moon closer to the Earth and further away from the Earth doesn't have to do anything, right? It's not part of the process. But the fact is that I have changed how the Earth looks from space by doing that.
But if I just touch the plate and allow the electrons from my hand go into the plate, then it can discharge it.
Right, so discharge just means now it can go back, okay, to the state where there's an equal balance between the electrons and the protons, their pressure, and everything looks to everything else like it's purple. So he was in a red state and now he's going back to a purple state.
So this effect that you're seeing right now is called the photoelectric effect. And it's actually what won Einstein his Nobel Prize.
Well, again, he didn't invent the effect, so he invented an interpretation of the effect, a description of it. So let's understand, Einstein didn't do this experiment. He heard about the experiment and then described why it was happening.
So if light were only a wave, then that means that it doesn't matter what the frequency of light is that you use. If you just use enough of it, then you should be able to knock electrons loose. For example, if you just...
This is where they're so stuck on their interpretation that, there's no way to intuitively say that's what you would expect, because then we're back to tipping point arguments, right? I mean, it doesn't matter how many rocks I throw at, say I want to knock something over, and it's gonna wobble, and then it can fall over. I know I have to add the energy in resonance, okay? I have to throw a rock, and when it's moving, I can let it swing back, and then I can hit a rock again, and I can add energy. But if I ever throw a rock when it's moving towards me, then I'm going to defeat the purpose. All right, now I'm going to lose my tip. I'm going to lose my wobble. All right, so the idea is that we know that's the systems are dependent on. So I'm just saying they're just ignoring that whole kind of thing and saying, oh, well, if it's a wave, the wave should just, it doesn't matter what frequency it is, it should be able to add energy to the system. Well, adding the energy to the system has to be in some way connected to resonance. That's why there's a frequency. I mean, I just can't believe the physics is this stupid not to concede there's this incredibly intimate relationship. I mean, the the obvious genetic similarity, however you want to describe it, the fact that they have to have the same lineage between frequency and resonance, and the idea of adding energy to a system. So, this is why I say this is such a poor argument. Even though it's an argument, I wish you to understand that the energy is quantized, that the energy does come in clumps. This is a terrible logical description. It's a terrible argument. And so I have to just point out it's a terrible argument, even though I totally agree with the conclusion that light is not a wave. This is a terrible argument against it being a wave.
Get a high enough amplitude and really big waves of light coming in, you should be able to discharge this plate. But
no, because you only have one speed to work with. So, again, it's just that this isn't about the volume of the push. It's about the fact that the only way to make the thing tip over is to hit it repeatedly. You can't do it with one push.
you can see that I used a 100,000 lumen flashlight here, and I couldn't do anything. So hitting
That's right, because of so this is part of what just should get people some idea that photons are composite objects, that this isn't just talking about throwing one rock at a wall and saying, there's the event, photon. You can't just throw one rock and that's the event. The event is clearly more complex than that, and all these experiments are just screaming that it's more complex than that. Single electron does not create a photon. It takes events that take place in sequence. That's why it's all about crystals. Crystals are what basically absorbing the energy, and what's a good way to say it? They're a catalyst for taking the energy that's happening in different places and putting it into one place. The seams between the crystals, you could argue, is where the energy, the electricity, the extra electrons end up. And the electrons are able to be transmitted. That's why a conductor works, is because it's a crystal. If it wasn't a crystal, it couldn't take the energy and move it to common roads to make it all go in one place from each crystal. So as each crystal expands and contracts, it's the seams is where all the action is happening, and that's where the electrons are being collected and added and subtracted and all that stuff.
Electrons with a bunch of low frequency light doesn't do anything to knock them loose. Whereas higher frequency light, like shortwave ultraviolet light, does have enough energy per photon.
So again, it's not per photon, it's not enough energy, all of this stuff. It's just the idea that if I was hitting something that was going up a hill, and so I hit it, it goes up the hill and then it starts to come back down the hill. You can understand that if I hit it with low frequency, it keeps going back down. I hit it, goes back down. Hit it, goes back down. Now, if I hit it with high frequency, I could hit it, it goes a little bit back down, then I hit it again. And then it goes a little bit back down, and then I hit it again. And it's going to end up going up the staircase. I'm going to end up being able to push it up, because each time it comes down, it's going to come down less than the amount I pushed it up. So I'm going to gain ground. Now, I won't gain a lot of ground, I won't get up fast, but I'll end up going up. And that's the point. That's what you're trying to do to an electron, is give it enough energy. So it's not even, I would argue, you're not even pushing the same electron. So on a surface, you're talking about, the atoms being in an arrangement, okay, positive, positive, you got your positives down here, and you got your electrons here. And what you're really trying to do is you're hitting this electron, it's going to move this electron, right? Because there's a force between these electrons that's repulsive. So when this electron moves, this electron's going to move. And while this one's moving, you hit it again. So that's the key part of it. Right now you're gaining velocity, because this one's going to go even faster than that one went, because it already has velocity in the direction you want to go. And the same thing's going to happen. You're going to push this electron with this velocity, and now you're going to add this extra velocity when you hit a third time here. So if we say it's 3 hits or 4 hits or 5, whatever a photon is, but that's a photon. A photon is this, a hit, 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 hit. That's the frequency. That's why the frequency matters. The photon is this object. It is not, this. That's not a photon. A photon is this, 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 this. You need more elements to it. So if you want to be stuck with a stupid wave theory, right, again, waves do this. They spread over surfaces. No, photons hit one little surface. Bang, 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 bang. One small surface, okay, that's just a few hundred atoms in size, but it's hitting at the right time for where the energy is going. So you could just, there's different ways to understand it, but like, again, if I have a surface, all right, and you could understand that in a sense, if I hit one electron here, it's going to, that electron getting pushed in would push on this electron, that electron, this electron, that electron, this electron, so we're going in any direction. And I hit it again here because I have a photon that's coming in pieces, okay, in phase. And this is its polarization. Well, it's going to hit the electron that's moving that way, and then this one's going to hit this way, and this one's, so it's sort of like a wave, like all of these are going out, but only one of them is going to get the second push, and only one of them is going to get the third push, and only one of them is going to get the fourth push. So this initial energy, okay, was essentially lost going this way, it just ripples out, all right, but this energy was added to. And that's why this electron pops out. Not this electron, this one here. This is the one that pops out because you gave it enough velocity to escape. And that's what's happening. Electrons don't make photons. Single electron can't make a photon. It has to come from numerous ones, and that's why the light is polarized. It's basically the atoms are the antenna. You need like 100 atoms or 1,000 atoms to make an antenna to create a photon, because the photon has to have spacing between the bits. It has to have a polarization. So the irony is, so this is another part I could criticize, is the part of the photon that matters isn't the frequency, in terms of kicking an electron. You could argue that something just as important is the polarization. So you know that, well, you should know that the polarization is proportional to the antenna size, and the antenna size would be the wavelength, would be proportional to. So, you have low frequency, you need a very big antenna. High frequencies, you need a small, like microwaves, little 3-inch antenna. Okay, I mean 3-centimeter antenna. So you go to higher and higher, and you get a smaller and smaller antenna. So infrared, I mean red light versus, well, infrared versus ultraviolet, you're talking about a doubling in the, in terms of the size. So the infrared would be this size, and the ultraviolet would be like 1/3 that size. So it's a much smaller polarization. So what does the polarization mean? That actually has to do with when you're hitting it with your 4 little elements, it has to do with the fact that you're hitting it in a smaller amount of space. So you could sort of understand that, if I'm hitting this and there's much more distance that everything's traveling, there's much more opportunity for it to fall back, fall back, fall back. But the closer I make the little bits in frequency, what I'm really doing is hitting closer. I'm hitting elements before the electron has moved very far. So I'm hitting them closer, which means I'm hitting, let's see, I mean, if I drew this, the up the hill thing, you can just understand that if I have a higher frequency, when I hit it and I move it, it has less time to fall down if my frequency is higher. That is, if I'm hitting it, and I'm going to hit it progressively. I shouldn't even use the slope hill. I should just use the flat surface. And so I'm going to hit the electron, and before it, let's say, slowed down from friction, I'm going to hit it again. So then it retained more of its velocity when I hit it again. And then I hit it again. Where if I let it slow down from friction and then hit it again, I'm not going to be adding as much energy. So because the polarization is small, that's why there's more energy per square inch, so to speak, more energy going in. So the whole argument could be is the polarization is more important than actually the frequency. But the point is that they're obviously connected to each other, so blaming one or blaming the other doesn't really matter. I mean, blaming the person shooting the gun versus blaming the gun, you know, the two things, they are connected to each other. But it's important to just recognize that it could be just that you're hitting more of your little bits or hitting a smaller surface. And so that means less time, and it means that energy is in a smaller container and therefore has more potential because it's in a smaller container. There's more pressure because it's a smaller container. That kind of argument could be made. So the smaller the surface you're hitting, the higher the energy. If you're hitting it with the same bullets, even. I'm making there's more density of holes being created in a target with bullets, the smaller the area I hit. You know, I don't know. So I'm just saying you could equally blame polarization for the fact that the smaller the polarization, the higher the energy.
Photon. So even if you have a really dim ultraviolet light, you can still knock electrons loose. The brightness and dimness of the ultraviolet light only affects the rate at which the electrons are knocked off, but it doesn't affect the ability to knock them off.
Well, yeah, but it also affects how aggressively you knock them off. So the speed of the electrons that you knocked off, that is how far away they'll go, is changed based on the frequency. So if you hit it with X-rays, you'll have electrons leaving at very high speeds versus the electrons you hit with the weaker light. So there will be a difference. It's not like it's all the same thing.
You can actually do this a little bit easier if you don't have an electroscope like this, but you just have a small neon light bulb. So my neon bulb's right here, and you can see that if I increase the voltage, right now we're at 6.
So it's kind of funny just because it's obviously people aren't going to have one of those sitting around. And you know, a voltage source to be able to pump, you know, 40,000 volts into it.
57 volts. Right
Well,
when I get
57.
around 89 volts, it'll turn on.
Right, and the fact that it turns on, that it's all or nothing, you know, is just the fact that you have to do this thing where it has to get hot enough for the electrons to fly all the way to the other surface, and, you know, to leave the surface.
There it goes. So I have to have at least this voltage to turn it on. But now if I get it to, let's just put it at 88 volts. Okay, so the light bulb is not lighting. The way these neon bulbs work is there's 2 electrodes in here, and in order to get light to occur, it has to strip the electrons off of the gas that's inside of there. So right now there's...
So it has to make the gas conductive, and it's just the same thing as saying it's putting a bunch of little bits through it. It's like heating it for... It's like setting it up for a lightning strike. Okay, there's a thing that happens before the lightning happens. The ionization of the atoms in between the clouds and the ground. So it ionizes the air first, and then the lightning can travel through the ions.
Not quite enough voltage to start stripping the electrons off, but we can actually induce those electrons to...
So he's just going to ionize the air between them, actually. So they can do this same thing with, you know, those towers, you know, the electric tower thing, whoever it's called, Frankenstein kind of electricity stuff, you know. And you can do the same thing by introducing anything that ionizes it. So you can introduce a candle, or you can introduce some other energy source that ionizes the air, and then you'll get your spark. And once the spark happens, obviously it doesn't need an ionizer anymore, because now it's ionizing the air through the heat of the spark.
Start being stripped off just by shining that shortwave ultraviolet light at this light bulb. So you can see it doesn't light, but now let's turn on our light bulb. And it turns.
So the interesting thing is he probably should have taken his big million lumen flashlight and shot it at there, see if visible light would cause the same effect. Because visible light might be able to ionize atoms, okay, enough, okay, because it doesn't need to give the electrons a high voltage, you know, it doesn't need to give them launching speed, it just needs to give them elevated ionizing energy. So the ionizing energy might be sufficient to have changed the atmosphere, because you're just changing the atmosphere.
Turns on. And once I start it flowing, it actually keeps flowing. I don't even have to keep the light on, because now it heats up a little bit so it can keep flowing. What?
Right, so I mean the heat is just causing the recreation of ions.
It's a little bit confusing about what I've been saying is I'm talking about light as though it were discrete particles, but then I'm telling you that it has a specific frequency. I mean,
see, the fact that he says it's discrete particles and it has a specific frequency, well, why can't that just mean the particles are at a frequency, right? I mean, he's sitting there saying it's very confusing for me to talk about me shooting a gun and bullets coming out, and they're bullets coming out at the same rate as I'm squeezing the trigger, and that the bullets at a rate would be the frequency of the quanta, the clumps. I mean, he's saying that's too complicated. Nobody could ever understand that. It could never, that's incomprehensible. No. That's really comprehensible. That's really easy to understand. And the only thing I'm changing here is polarization. I'm saying I fire a bullet. A fixed amount of time later, I fire a bullet, but I fire it from a little different position, because we're really talking about electricity moving, right? So we're saying, here's the electricity moving through the conductor, right? The little pathway of atoms. Bang. Okay, and electricity moves to another ionized atom. Bang. Another ionized atom. Bang. Another bang. So it's banging from different locations. It's gaining enough speed to kick an electron. And the electron just kicks. That means it just does this. Bang. Then it has another electron. Bang. Moves out. And another one. Bang. Moves out. It's just doing this. 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 And this. And I'm just saying you do that from these different positions. Push here from an electron. 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 That's a photon.
The definition of a frequency is the number of oscillations in a given amount of time.
So, I mean, to say that's the definition of a frequency is almost just so bad. I mean, the fact that they have spread their wave whitewash on everything, and that now not even frequency can be understood as something that's not wave-like behavior. I mean, I could put a... You know, you could have a rigid tire, and I could make one side of it flat. You know, that's not a wave. Thump, 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 thump. That frequency isn't a wave.
But I'm talking about a particle. How does a particle have oscillations?
You just add more particles, and now they have oscillation between the particles. Yes, the grain of sand doesn't have a frequency. An electron doesn't have a frequency. Again, the very fact that they find it really easy to understand that, oh yes, an electron has a frequency. A Volkswagen goes down the street, it has a frequency. They think that makes sense, and yet they're saying it doesn't make any sense just to say there's 5 Volkswagens going down the street. They have a frequency.
It's not a wave. Well, to understand this, we have to understand what a particle even means. How do you define a particle? Now, this is
a thing that you can't break. That's a particle that doesn't break into its sameness. Okay, so I don't know how else to say it. I mean, obviously, the idea is you can't break an atom into 2 little atoms. Well, you can, but you know, they're still patterns inside. They're not the same atoms.
This is going to sound weird, but the actual definition of a particle is the possible smallest vibration of a quantum field.
Okay, so now isn't that just too disgusting to say that this makes any sense? That you're going to use the same word and apply this completely different definition to it, that a particle is some sort of vibration. I mean, what the fuck is that? Too silly.
And the photon, like the photons of light I've been talking about, is the smallest possible vibration of the electromagnetic field.
Yeah, whatever that is. So again, just saying smallest possible vibration, still it's saying absolutely nothing, because we know the vibrations are different. They all have different energy levels. So why are we saying it this way? It's horrible.
And then there are even other fields. For example, a quark is the smallest possible vibration of a quark field. So that's how a particle can still have a vibration, because we're still talking about a vibration of an underlying field.
Yeah, a vibration with limited, that doesn't go anywhere. So again, that is their image. That somehow there's friction in the ether or something, and somehow the wave runs out of energy somehow. And that this little blobby jellyfish thing, it's jellyfish all the way down. So somehow the energy is in the electron. It's good. It's doing this all day long. It's a little energy monster. And a little quark is a little energy monster. It's a little jellyfish. Who would do that to evolution? Who would do that to any kind of mechanical system? To sit there and say the energy is in that elemental piece when it's clear that doesn't make any sense. The energy is in the little shit going the speed of light. There's no energy in the electron. Oh, well, it's just too pathetic. And what's it waving? All these fields. What are these fields made out of? I mean, come on. Fields of what? It's fields of fabric, apparently. Two-dimensional fabric. Because, yeah, they can't make the three-dimensional drawing make any sense at all. Oh, this is just terrible.
But the vibration of that quantum field manifests itself as a discrete particle. This is why we have the wave-particle duality.
Yeah, it's because this is just too sick. Because you have a silly model and it doesn't work and it doesn't make any sense. Waves go everywhere. Photons don't. I mean, the thing is dead right from that alone. The very idea that there's the energy of the photon is going everywhere, and then it retracts all the everywhere energy and makes it all just go here instead. What are you talking about? Too silly. I just can't believe they can sell this to people and they buy it. I just can't. I can't believe they want to sell it in the first place. It's such crap.
Why sometimes light can appear as a wave and also appear as a particle.
It's particles that are waving. What's so complicated? Yes, particles that have a frequency. Yeah, oh, that's so hard to figure out.
Now, whether we talk about something as a wave or a particle kind of depends on its wavelength or its frequency. The higher frequency particles like ultraviolet light and X-rays tend to always manifest themselves as particles. So
this is just another too silly a point, right? I mean, they're obviously manifesting themselves in much tinier portions of space, and so therefore they're much smaller, so they're harder to see. So you're just calling them particles because you can't see them. That's it. I mean, it's like if I make the leopard spots on a leopard really small, oh, I can't see that there's spots anymore, so I'll call it one color, right? And if I make them big, then I can see them, and I'll say, oh, it's spot not spot duality, just because I can see them. And that's how bad this is as physics, as science, as vocabulary. The vocabulary is that silly. I'll call it a particle when I can't see the spots. That's just stupid.
We usually can't see the peaks and valleys of their waveform because they're too close together. So we usually call the higher frequency things particles. Whereas particles with lower frequency...
So and obviously the thing doesn't have a frequency. There has to be more than one thing for there to be a frequency. The thing doesn't have the frequency, and you can know it just by the illogic of thinking of the radio wave photon. Do you really believe it's a big blob of thing comes shooting out and it's miles and miles long? Or does it make more sense to say, no, I fired a bullet, then I waited a while, and then I fired another bullet? Which one makes more sense?
We usually just always call them waves. For example, radio waves have an extremely long wavelength and a low frequency. So we usually only see their wave properties and never their particle properties.
So again, that's just more nonsense. You can see it if you look for it. But obviously it's hitting giant surfaces. So yeah, it's really hard to see it because the particles now are much bigger than you. They're miles long, so to speak. The surface over which the little bits are hitting, the relationship of the frequency. Now you're too close. You're too close to the movie screen to see the movie.
In fact, we've never even been able to detect a particle of radio wave because a single photon in the radio frequency has such low energy that we can't detect it.
And so the same is true for the light. It's just that the light is so many more photons. So that's the difference, is the number of bits is so much more energy going to a surface than, you know, the radio. The radio is so frickin' diluted in the places where you're measuring it.
And thanks for watching another episode of the Action Lab. I hope you enjoyed it. If you did, don't forget to subscribe if you haven't subscribed.
La 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 la. Yeah, I unsubscribed for him from a while ago, and that's why I didn't see this video, because they were all crap videos, and it's all just this junk and commercials, and it's just disgusting. So I subscribed again, just in case he does do some kind of interesting experiment. Anyway. So that was pretty horrible in my opinion. I mean, that gibberish at the end was just so bad. To try to pile on and try to say how this is sensible physics, this frickin' wave particle duality nonsense, that there's any kind of sense in playing these games with words. Something is either a something or it's not a something. And the somethings have real motion in 3 dimensions. I mean, they've broken everything and turned it all into wooey nonsense. 4th dimensions. There's no 4th dimension. There's no way to connect a 4th dimension. Time isn't a dimension. It's a function. Stuff moves less than instantaneously. Oh, therefore there's time. Yes. If it doesn't happen instantaneously, then there's a lag, and when it's happening, and the lag is called time. Oh, but anyway, it's just, this is too, just so depressing. Anyway, so we'll call that a video. Just hell with it. You know. So anyway, but the charge thing is very interesting. It's all related to magnetism. Obviously, the atoms are becoming dipoles. You know, they go from being a non-polar to being a dipole to being a, you know, and obviously the monopoles are electrons and protons. They're the things really creating whatever you have. Their relationship to each other is causing the effect, and the effect is just a pattern in the case of light, and that's it. And then you go all the way back to gravity, and it all, the particle theory explains it all. There's just 2 kinds of force, 2 kinds of matter bit, electron and proton, and 2 kinds of interaction, and that's all you need, and you're done. You explain the universe. Instead, they do this mush. Convoluted mush. Shit. So, till the next time and such, this has been a DraftScience video presentation. Yeah. The counter arguments will be, fuck you. Yeah, okay, fine, whatever. Nice try.